So what I want to do today is I want to do a bunch of problems that will illustrate a lot of the key concepts that we've been doing all semester. So the first one was the following game. I give you some number, say 100, and I want to write 100 as a sum of non-negative integers. Well, actually, I'll do a little bit better. I'll say positive integers. AI are positive integers. And the goal is to maximize the product A1, A2, AN. So why do I say I want them to be positive integers? Yes?
Because you could go to infinity if you were just adding and subtracting.
Good. So if I allowed myself to have negative numbers, I could make my product arbitrarily large by putting in 200 and negative 100. And just playing a game like that. So if I allow myself to have any values for the AIs, it's not going to be a well-defined problem. Why don't I want any of the AIs to be 0? Same thing. Then the product is going to be 0. Okay. So again, the reason I want to do this is not only is it going to review a lot of our material, but it's a good way of thinking about how to attack problems you haven't seen. Can anybody give me any information about the values of these AIs? I don't care how stupid it is. What kind of information can you tell me about the AIs? What possible values could they take on? 1 to 100. So first, we know 1 less than equal to AI less than equal to 100. Can you improve this a little bit? Yes?
It's got to be less than 100, or else if one of your terms is 100, then there is only one term.
Okay, so then maybe that's the best. Maybe the best product you can do is 100. So you have to prove to me that that's not the best case to have just one term of 100. Can you prove to me that that's not the best case? I'm sorry?
In a specific case?
Well, you just have to prove to me that I don't want to have everything being 100. So there's lots of ways to prove that. So I think you were saying it. 50 times 50. So if we know it is 50 times 50, we know we're not going to have everything be 100. What about 1? Do we want any of the AIs to be 1? It doesn't help the product. If you have any of the AIs be 1, fold it into something else. So we know 2 less than equal to AI less than equal to 100. And now we want to really play on this. So it's already been suggested that we don't want to go up to 100 because we could do better with 50 and 50. But what about 99? Well, if we had 99, one of the numbers would have to be 1. That would fold in, so we don't want a 99. What about a 98? Would you want 98 as a product? Why not?
Because it's still really small, like 98. Like you could do times 2.
Okay.
And then that's still 200, like less than 200.
Well, but you have to prove that you can do better than just having one of the numbers be 98. Well, let's jump a little bit into the future. Let's say I claim that one of my numbers is 16. Can you prove to me that you would never have a 16 in the decomposition? What could you do if you had a 16 as one of the terms? So I want to maximize the product. Imagine one of the terms was 16. Can you come up with something better? I haven't told you what the other terms are. I've just told you one of the terms is 16, and you can have as many factors as you want. Yes?
So, if... Oh, no, I had fun that I thought it was...
Right. So what could you do if one of your terms was 16? What could you replace it with?
2 8s.
You could replace it with 2 8s. And the product is bigger. 8 times 8 is 64. So just to make things a little bit easier, rather than replacing with 2 8s, I just have to replace it with something better. So never have 16, because I could replace that with 13 times 3. That's going to do better. Would I ever have a 17? What could I replace 17 with? So I could do 15 times 7. I'm always going to keep my 3 here. The reason I want to use the 3 here is if I replaced 16 with 8 times 2, that would actually be the same product. But if I do 13 times 3, it's better. 17 is 14 times 3, it's better. 18, what would I do with 18? 15 times 3. So we can see we're never going to have any of our terms 16, 17, 18, 19. None of those numbers will ever occur. What about 15? What would we do if we had 15? So what would we replace 15 with?
12 by 3.
12 by 3. So let's keep going down. How far do you think I can go down? Bless you. Could we do 7? 4 times 3. What about 6? 3 times 3, okay. 5.
2 times 3 is better.
I'm sorry?
2 times 3.
2 times 3 is better. What about 4?
3 times 1
So can we do anything better with a 4? But we can still break it up. And even though it's actually the same, and I'll write an equal sign here, I actually prefer to do this. Yes?
You mean 2 times 2?
Oh, sorry, 2 times 2. Thank you. I actually prefer to do this decomposition because now I can say that the only numbers I have are 2's and 3's. Because anytime I have a 4, I can split into 2's and 3's. So we can now deduce, in fact, that each AI is either a 2 or a 3. We don't have anything else. We just have a question of how many 2's do we have, how many 3's do we have. Okay? What do you think? Yeah, question.
But what about, like, 13?
Well, if we had 13, we could write 13 as 10 times 3. So we can split the 13 as a 10 plus 3, and that will give a larger product. So we're only going to have 2's and 3's. Now, right now, you might be wondering, why is this in a calculus class? Right. It will eventually make sense as to why we're doing this in a calculus class. A little patience. I think I've earned it this late in the semester. All right? Do you think we want more 2's or more 3's? Which do you prefer?
2.
Why 2's?
I mean, because we kind of like kept making them smaller.
Okay.
So it would make more sense.
So it would make more sense to keep making smaller.
Yeah.
Does anybody know the conversion rate between 2's and 3's for this problem? How many 3's equal how many 2's? Remember, it has to sum to 100. Yes?
2
Let me say it again.
Every 2 3's is 3 2's.
Excellent. Every 2 3's is 3 2's. It's tough to say. All right? Why? Because 3 plus 3 is 2 plus 2 plus 2. So at this point, I can now erase this whole table, because we don't need this anymore. We know we never have any of these numbers, so let's get rid of them. Imagine you had 3 2's. What's the product of 3 2's? 8. What's the product of 2 3's? 9. So every time you have 3 2's, you would replace it with 2 3's. So your answer is going to be essentially all 3's and either 0, 1, or 2 2's. So the answer, and I'll leave this to you, is all 3's except 0, 1, or 2 2's. And then you can just figure out now which one of these is going to be best. Okay? So what I like about this problem is, at first it seems very hard how you would attack something like this. But if you whittle it away, if you keep thinking about ways to look at it, you can get a lot of information, and then you can reduce to a very simple problem of just which is better, 2's or 3's. Does anybody know any important numbers between 2 and 3?
E.
E. E is about to make an appearance in this problem. And that's why this is a calculus problem. How many of you have taken a comp sci class? What base do computers like? Binary. Computers love base 2. I am actually going to show you a reason today why computers would prefer for some things base 3. There is an advantage of base 3 over base 2. And it all comes down to the fact that E is closer to 3 than it is to 2. E is 2.718281828. It's a little bit closer to 3. And that's going to have profound consequences. Okay, is everybody okay with the first part of this problem? What I want to do now is I want to look at what happens if we change it a little bit. This is not a calculus problem because I'm forcing everything to be an integer. This is a number theory problem. I love teaching number theory. I'll be teaching it next year, but that's not what I'm supposed to be teaching today. I'm supposed to be teaching calculus. All right, let's make this a calculus problem. All we do is we see this word that's on the other side of the line. It's not a coincidence. It's not supposed to be there. We just require the AIs to be positive. Now that we have the AIs positive, the goal is to maximize this. Given that they sum to 100. How much of our analysis from before is still valid? Could we have a 16 as one of the terms? No, we can still break 16 as 13 plus 3. What if we had 12.5? Could 12.5 have been one of the terms? No, we can break it as 9.5 and 3. The analysis as before follows. So, as before, only have numbers between what and what? Between 2 and, be careful now. Between 2 and what? We don't know E yet. So when we were breaking things up, we could break up the number 6 as 3 plus 3. We could break up 5 as 2 plus 3. We could break up 4 as 2 plus 2. And then we said, well, we're indifferent between having a 4 and having 2 2s. And then we said, well, then it has to be just 2s and 3s because they had to be integers. But now they don't have to be integers. So they're between 2 and what? 3 is going all the way down to an integer. Remember, we said we had 4, and we were indifferent between 4 and 2 plus 2. What if we go to 3.99? If I try to break this up, if I try to break it up maybe as a plus 2, I've got 1.99 and a 2. And now when I multiply, it's actually a little bit lower. So I've got to be careful. So it's between 2 and 4. That's the range where I know things. So I can go over here now, and I can say, I know each AI is between 2 and 4. And I want to figure out what's the best way to break it up. The problem is, I don't know how many pieces we have. That's what makes this problem so difficult. If I told you, break it up into 2 pieces, how do you think you would do it as 2 pieces? 1550. Where have we seen this before?
Farmer Brown.
Farmer Brown. This is the Farmer Brown problem. If n equals 2, it's the Farmer Brown problem. You have a perimeter, and the goal is to maximize the area. If you want, one way of looking at it, if you now take n equals 3, is you basically say you're going to have some kind of rectangular box, and you want to have a fixed value for the sum of the length, width, and height. Maybe. And then you want to see what's the largest volume you could get for a given corner frame. So the question is, how would you do a problem like this? What should be in the back of your mind? I'm sorry, the lambda stuff, also known as Lagrange. Okay. What letter of the alphabet does lambda correspond to?
Starts with an L.
L. Have no idea if it's because of Lagrange, but yeah. So maybe that's why we use lambda. So we want to try to figure out how to do this. So there's two levels of maximization here, two levels of optimization going on. It's going to be a two-step process, and in doing this, we're going to review almost all of Calc 1 and 2. Well, I guess maybe just one Calc 1. First, I'm going to fix a value of little n, and I'm going to see what's the best I can do for a fixed value of little n. Then I'll vary little n. Okay? So step 1, fix n, find best. And then step 2, vary little n, find best. So it's a two-step optimization problem. Okay? So for step 1, we fix a number of terms. Maybe it's 5, maybe it's 20. What do you think is the best we can do if we have to divide it up into 10 pieces?
10.
I'm sorry?
10.
10. Now I just realized this is a horrible number to say because 10 and 10 go so many different. Let's say we want to divide it up into 20 pieces. How much should each piece be? 5. Divide everything equally. So here is step 1. Maximize x1, x2, xn subject to x1 plus xn equals 100. Is there anything special about the number 100? So I can do this for a more general number. Okay? Do you want me to just keep doing it for 100 and then at the end of the day we can say 100 equals s? Or do you want me to just put an s right now? Put an s. Has nothing to do with my name. Okay, we'll put in an s here. We'll put in an s here. Alright, so how do we set this up as Lagrange multipliers? We need a function and we need a constraint. So what's the function? So we need f of x1 through xn. What should my function f be?
I forgot the
First word starts with math symbol. Sounds like
factorial. That, yeah.
factorial.
Factorial.
What factorial?
Sorry? No, it's not x factorial.
Not x factorial. It's kind of like a factorial. What should my function be?
All the x's multiplied together.
Yeah, all the x's multiplied together. I'm trying to maximize this subject to this. Here's my function x1, x2, xn. What's my constraint function?
x1 plus x2 plus xn equals s.
Or minus s equals 0. You can do it either way. Is this within range of the camera?
Oh.
No, it is. I know. No, I made a comment about it. Okay. So now, we have our function, we have our constraint. We take the gradients. So the gradient of f at x1 through xn. Now when you take the derivative of this with respect to x1, what do you get? All the rest of them. Alright? So it's going to be a little painful to write. I'll have x2, x3, x4 all the way up to xn. And then the next one will be x1, x3, x4 all the way up to xn. And the last one will be x1, x2 all the way up to xn minus 1. There's a really nice way to write it. And it's going to be the following. x1 times xn times the vector 1 over x1, 1 over x2, ... 1 over xn. So this is just doing some algebra to write it in a better way. Why? Well, when I multiply this in, what do I get? I get the product of everything divided by x1. Hey, that's everything but x1. When I bring it in and I divide by x2, I get the product of everything except x2. This is just a really concise way of writing it. You might remember on one of the midterms, I gave you the gradient of some functions, and I asked when were they aligned with each other. And I said we can just pull out this number and they're equal to something in the direction 1, 1. Foreshadowing for later in the semester. Okay, I can just pull out this product x1 through xn. Any questions about how I do this derivative? If you're uncomfortable with it, just do the derivative the right way, and then note that I multiply by 1 in the form of x1 over x1 here, and pull it out. And so if you want to do it that way, and you cleverly multiply by 1, that's fine as well. The gradient of g is significantly friendlier. What's the gradient of g? Gradient of g. All 1s. So now we're going to have to set them equal. So we need the gradient of f to be lambda gradient of g, and we need g of x1 through xn equals 0. This is how we do Lagrange multipliers.
So how do you know that they're all ones?
My function is x1 plus x2 plus x3 plus xn minus s. So when I take the partial with respect to x1, I just get 1. When I take the partial with respect to x2, I get 1. So the gradient is going to be just the vector of all 1s. Okay? So, yes?
Sorry, why do we set g equal to 0 and
That's
not
just,
s?
that's just a constraint.
Why do we
I define g to be x1 plus xn minus s equals 0. If you wanted to, you could have defined the constraint to be the sum of the x's equals s. And that would have been fine as well.
Why did you subtract s?
I like having my constraints equal 0.
Oh, okay.
I like having my peanut butter on top. There's just some things that don't really matter. That might be too much information, but there are just some things that don't really matter, and you can choose which way you want to do things. If I had set this equal to s rather than equal to 0, would that change the gradient here? No. And all that would change is this 0 would be an s. It would be a slightly different function. You would have almost identical algebra. To me, I just like having the constraint today equals 0. Almost surely in other days I've done it the other way. Doesn't matter. Okay, so now we're going to continue with the camera work and pushing you over. And so now we're going to come over here and actually solve. So we want x1, x2, dot, 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 xn times 1 over x1, 1 over xn equals lambda 1, 1. And we want x1 plus xn minus s equals 0. What do we know about the xi's? What's the one thing I always worry about? Whether or not they're 0. Well, if any of the xi's was 0, the product would be 0, and that would not be a maximum. So I can assume all the x's are non-zero. Well, I'm also writing reciprocals of the x's here. They better not be 0. Okay? So we can say all xi's are non-zero. Okay, so now we need to solve. Well, I need this vector to equal this vector. What can you tell me about x1, x2, x3, x4? What must be their relationship to each other? Yes?
Equal.
They all have to be equal. If you take the ratio of the first term over the second term, and you take the ratio of the first term over the second term here, you'll get 1 over x1 divided by 1 over x2 equals 1. So from ratios, so for example, x1, xn times 1 over x1, x1, xn, 1 over x2 is lambda over lambda is 1. So we get 1 over x1 divided by 1 over x2 is 1, x1 equals x2. Was there anything special about x1 and x2? Could I have done the ratio of the first and the third? The first and the fourth, the first and the fifth? They all have to be the same. The other way of looking at it is this vector has to be in the same direction as this vector. This vector is in the direction 1, 1, 1, 1, 1. So the only way that can be in the same direction is if all those components are equal. Okay? So there's lots of different ways you could do this. Instead of looking at the first ones, we could do xi and xj, and we would then get xi equals xj. So they're all the same. Okay, if you now know that they're all the same, what must their value be? I'm sorry?
4.
Why 4?
We're anywhere between 2 and 4.
Well, they're between 2 and 4, but that's not enough to know that they're 4.
Yeah, I realized that.
Okay. What value must they take on? So remember, in Lagrange multipliers, we have more than just the gradient of f is lambda gradient of g. What else do we have?
The constraint.
The constraint. Well, the constraint tells us the sum of the x's minus s equals 0. Well, all the x's are the same. So use constraint. We get n times any one of them minus s has to equal 0. So what does each one of them equal?
S over n.
S over n. So that finishes step 1. So in the case when we know that there are n pieces, the best we can do is to make each piece 1 over n of the total. This is what you would expect. Divide everything equally. That's going to maximize the product. Okay. Any questions about this? Yes?
I don't get, like when we did the ratios part, like exactly what is happening.
Well, we're trying to solve this. We're trying to figure out what can we say about the x's to make this true.
Okay.
So when we do Lagrange multipliers, if we take ratios, we eliminate the lambda, which is good. And we'll eliminate this product, which is good. So if we look at the, this is n equations. So I'm just unpacking the n equations. This is the ratio of the first equation to the second equation.
Okay.
Right? The first equation is this product equals lambda. The second equation is this product equals lambda.
Okay.
So their ratio has to be lambda over lambda. Does that, you still seem a little hesitant.
Yeah, I
So let me write it out a little bit longer. Let's say I have 3x, 2y equals 4, 5 with a lambda. Then that means 3x equals 4 lambda, 2y equals 5 lambda. Therefore, 3x over 2y equals 4 lambda over 5 lambda. That's exactly what we're doing here. We have n equations. The first component equals this. The second component equals this. The third component equals this. So the only way they can all be equal is, it turns out, if all the x's are the same. The other way is you don't have to do the algebra. You could just look and say the only way they're going to be the same is if this vector is in the direction 1, 1, 1, 1, 1. This is the vector all of whose components are equal, so this must also be the vector all of whose components are equal. That's a higher way of solving the problem that requires you to notice something. This is more just brute force algebra, just work through the algebra.
I just missed, how did you get the gradient f? What were you doing with
To calculate the gradient of f?
yeah.
Well, when you take the derivative with respect to x1, you'll then just get x2, x3, x4, all the way up to xn, that product. That's the same as the product of everything divided by x1.
Okay.
Similarly, if I want the last term, it's going to be the product of x1, x2, all the way up to xn minus 1, which is the same as the product of everything divided by xn.
I was going to ask a similar question. Like, it just seems to me there like you're dividing. Seems like that would just be 1 now.
Which over here?
Yeah.
Well, when you bring this factor in, you're going to get here. Let's do that a little bit slower. So df dx1 is going to be x2, x3, dot, dot, xn. Because I keep everything fixed but x1. Well, I can now multiply this by x1 over x1. And now I see it's the product of everything divided by x1. Similarly, if I take the derivative with respect to x2, I'll get the product of x1, x3, x4, all the way up to xn. Then I multiply by x2 over x2. So it's just a fast, clean way of doing the algebra. Okay. Any questions so far on step 1? And again, please ask questions. The whole purpose of this is a review.
So then, but I thought the purpose of this was you didn't have x1 in the numerator.
Right, but now I'm going to have the same factor hitting all these different terms. If I don't do something like this, I'm going to get my gradient is x1, is x2, x3, xn, then it's going to be x1, x3, xn, all the way down to x1, x2, xn minus 1. And I'm going to then have to work with this nightmare equals the other thing. It's going to make the algebra a lot harder. I'm using the fact that I have been working on this problem for longer than you've been alive to know how to formulate the algebra in a nice way to save time at the next step. You know, I wouldn't give you something where the algebra is this bad on an exam and expect you to be able to do it. But knowing this, knowing that I can factor things out. The sad thing is, as you go higher in mathematics, really it's the ability to do basic algebra that makes the difference. Is can you see an expression and can you find a good way to look at it? And so it's just, notice that these terms are almost all identical. And if I just pull out that common factor. Okay. Other questions on step 1? We're halfway there. Okay? Now it's time for step 2. We want to vary the n and find what's best. So I have some function, I'll call it v of n is going to be s over n to the n. This is the best you can do with n pieces. Because we just showed that if we have n pieces, what we do is we assume we show that all the pieces had to be the same. And now we want to figure out what n makes things best. What would you love to do to figure out what makes things best? Take the derivative. Wouldn't that be a wonderful thing to do? It's a calculus class, we should be doing derivatives. Why can't I take the derivative of this? What prevents me from taking the derivative of this?
You have the constraint.
I'm sorry?
Since you have the constraint, you have to kind of compare it.
Well, I don't have a constraint. I have a constraint, but what's the constraint on? What does n have to be? Anybody know the Bible? This is an acceptable way to use it in a class. I'm not saying it's correct or not. Anybody know the story of Solomon and the baby? What was the proposed suggestion?
You can't cut the baby in half.
Well, that was the proposed suggestion was to cut the baby in half, and each mother gets half the child. Mathematically, it's a nice solution. Okay? There are some technical difficulties if you try to cut the baby in half. Do not go home and explore this, okay? But I'm not advocating something like that. You can't cut babies, you shouldn't cut babies in half. N must be an integer, right? Just because this is going to be on the web, I want to be very critical of myself, okay? So if you learn nothing else this semester, okay?
Underline the do not.
Yes. Right. If you want to cut a cantaloupe, that's fine. Okay? N must be an integer. Can I do calculus with integers? So, cannot do calc as n is an integer. Oh, sorry, not happy face. Happy face, right. What can we do? So n has to be an integer. Can't cut the baby in half. So
We can do a sum. No.
we don't want sums, we want calculus. Search and replace. Consider the following function. Now, if x happens to be an integer, then that's the function we want to study. So what we want to do is we want to figure out where is the integer maximum of this function. It turns out, and this is a huge subject, trying to find integer maxima of functions is extremely difficult. Finding maxima is easy. This is calculus. We have the method of divide and conquer. We have Newton's method. We have find critical points. We have lots of ways to maximize functions. Typically, we don't have ways to find where an integer valued function is best, or a function on the integers is best, unless you're in a very special situation. If you're in a situation of a mountain, you're okay. So in a situation of a mountain, imagine you have a function that goes up and goes down. If you can find the absolute highest point on the mountain, where's your integer maximum going to be?
The closest integer to the peak.
Not necessarily closest integer. You're very close though.
If you round down to the closest integer.
Maybe, but it might not necessarily be rounding down. So maybe, depending on how sharply things are, maybe here is the integer 40, and here's 41. And so here, the maximum is occurring right here. The closest integer is 40, but the largest is actually at 41, if I restrict myself to integers. So how many points would I have to check? 2. 2 points to check is not bad. Okay? So in a very special situation when it goes up and then down, there's only going to be 2 candidates for the integer maximum. So we'll be able to use calculus. We just have to figure out how to differentiate this function. And this is another reason why I love this problem so much, because this is a fun function to differentiate. Anybody know how? So this gives me the function x to the x. How do you deal with something like this?
Chain rule?
I'm sorry?
Chain rule?
You can do the chain rule, but you're still going to have to figure out what's the derivative of x to the x, and it's not x to the x minus 1.
You do logs.
We can do logs. Whenever you see a product, take logarithms. Or you could convert this to an exponential. And you could say this is e to the x natural log of s over x. Or instead of trying to maximize this function, I could try to maximize the log of the function. Or I could let w of x be the log of v of x, which is going to be x log s over x. Doesn't really matter which one you do. Both of them are good techniques. I'm going to choose to do it this way because this will allow me to have some fun taking derivatives. Okay, so what would v prime be? So again, this is a way to just practice our calculus. I have e to the x log s over x. And in fact, you can even write that as e to the x log s minus x log x. The log of a quotient is the difference of the logs. So what rule do I use to take the derivative of this? So what would I do to take the derivative? The chain rule. But it's the one-dimensional chain rule, so it's not nearly as bad as the higher. So v prime of x is going to be e to the x log s over x. And now I need the derivative of x log s minus x log x. So again, I'm going very slowly so I don't make any calculus mistakes. Okay? So I get v prime of x is e to the x log s over x. And now I have the derivative of this. What's the derivative of x log s?
X. Isn't S a constant?
S is a constant.
So it's just X.
Not
Oh.
Of s.
log of s.
What? Oh, right. Yeah,
Right?
whoops.
Log of s.
Whoops.
Now I have to take the derivative of x log x. That's the product rule. The derivative of x is 1, so I get log x. And then the derivative of log x is 1 over x. X times 1 over x is 1. What am I trying to solve? What am I trying to find? So what do I need to look for? So I need to solve for what? What to be 0?
This derivative?
The derivative, right. So we want to solve for v prime of x equals 0. Okay? So this is going to be a nice algebra problem to look at. So now, I can move the camera over. And so we now get v prime of x equals 0 means e to the x log s over x times Now, there's a nice way of writing 1. I can write 1 as the log of e. So I get log of s minus log of x minus the log of e equals 0. And I'm writing it as the log of e to just simplify the analysis. Well, can e to this quantity ever be 0?
Nope.
No. So I can just remove this, and now I can combine the logarithms. So I get the log of s minus x minus e, so it's x, so it's the log of s divided by xe has to be 0. What number has a logarithm of 0?
1.
1. Therefore, s divided by x over e equals 1. Therefore, x equals s divided by e. So what it's telling you is that if you want to divide your number up, the number of pieces you want to have is s over e. That's how many pieces. And each piece is going to be s divided by s over e equals e. So what you want to do is you want to divide your number up into e's. That's the best you can do. And it turns out, I'll post an article. In terms of storing information on your computer, base 3 is more efficient than base 2 for storage because e is closer to 3 than 2. In terms of actually doing algorithms on the computer, in terms of actually programming and building the damn system, base 2 is much better. On, off is much easier to work with. But there is an advantage of base e. So this is a non-trivial calculus problem. Right? In fact, it's a Lagrange multiplier, followed by a Calc 1 problem. All we have to do now is show a function goes up and then goes down. So now it allows me to do the final step, which is curve plotting. Is it still visible down here? Or
Yeah,
no?
now it's good.
Okay, so here's how I like to plot things. Here's x, here's f prime of x. Okay? Here's 0. The key point is when x is s over e. What is f prime at s over e? So what's f prime at s over e? It's, somebody say it louder. 0. What is f prime if I'm greater than s over e? So we've got to look over here and see what's going on. So my function, f prime of x, v prime of s is e to the x log s over x times the log of s divided by x times 0. If x is greater than s over e, what can you tell me about the derivative? Positive or negative? So give me a number larger than s over e. There's a really natural number larger than s over e. Let's take s. If I take x equals s, then I've got the log of s divided by s. See, this is the log of 1 over e. Is the log of 1 over e positive or negative? So the log of 1 over e or the log of e to the minus 1? Negative. So my derivative is negative for x larger than s over e. This is a skill that is not taught nearly enough anymore. It's just general curve sketching. A lot of times they force you to draw cubics and whatnot like that, get the points of inflection and all that. You want to have some rough idea of what's going on, especially when you have arbitrary parameters. I want a rough shape of my function. There's a reason why you're supposed to learn these techniques. If x is large, v prime is negative, my function is decreasing. What if x is small? What if x is like 1, so I have now the log of s over here, I have the log of a number greater than 1. Positive or negative? Positive. So this tells me my derivative is positive from 0 to s over e, and then negative beyond that. So my function has to look something like this. I am not going for an art prize. I'm just trying to get some rough flavor of what my function looks like. It goes up, it goes down. It doesn't go up, down, up, down, up, down. It doesn't oscillate. It goes straight up, straight down. So if this is the best value I can take, then the integer best, all I have to do is just check the 2 points on each side. Okay? So this is an extremely involved problem, but it is a great way to review almost everything we've done all semester. Okay? Any questions on this? Yes?
How do you go from e of x equals sum over x to the x, to the e of the x?
How are we going to go from this to here?
Yeah.
Okay, so the way I went from here is I said, I want to write this as e of something. So I'm really solving the following equation. S over x to the x equals e to the u. Let's solve for u. So how do I solve this? If I take the log of both sides, I get the log of s over x to the x equals u. And now I just use my log laws. The log of something to a power is the power times that log. So you get x log s over x equals u. So this is an extremely useful technique that if you have a function, you can rewrite it often as an exponential. And now you can use the chain rule. We know the derivative of the exponential function. We do not know the derivative of x to the x unless we do something involved like this. Other questions? All right, so since we just have, I think we have like 2 or 3 minutes left, well, 4 minutes. What I will do is, I'll do another application of this idea right now to show you that you have almost surely had somebody slip something by you in a calculus class. So I want you to give me the derivatives of certain functions. Okay, so here's the function, here's the derivative. X squared.
2x.
Okay? X to the 1/2. X to the square root of 2.
1/2 x to the negative 1/2. Oh no! Oh god, it's not my day today. I was. Yeah.
So the question is, why are these true? So, how many of you remember how you proved the derivative of x squared is 2x? What did you use? Definition of the derivative, and you expand out x plus h squared. And you use the Binomial Theorem. And in fact, this works not just for x squared, it works for x to the n is n, x to the n minus 1, for any integer value of n. If I take 1/2, I can't use the Binomial Theorem, because that requires me to expand x plus h to the 1/2. How many of you actually proved the derivative of x to the 1/2 is 1/2 x to the minus 1/2? Yeah, the teachers just kind of slipped that by you. That, you know, the proof you did only worked for integer values of n. And then suddenly, somehow, you forgot that you only proved it for integer values of n, you just kept using it. The way you do it is if you let f of x be x to the 1/2, let g of x be f of x squared. What's f of x squared? X. And now we can use the power rule, and we get g prime of x is 2 f of x, f prime of x equals 1. So we get f prime of x is 1/2 1 over f of x. F prime of x is 1/2 x to the minus 1/2. That's what you have to do if you want to prove the derivative of x to the 1/2. If I gave you x to the p over q, you could do this as well. So all that would change is if I now give you p over q, you get p over q, x to the p over q minus 1. What do you think I look at? Instead of g of x equals f of x squared, I look at f of x to the
Q over p.
just to the q. That will give me now x to the p. And now I'll get a q f of x, f prime of x, x to the p minus 1. And now you just go through and you finish the algebra. And so this is how you would take the derivative if I gave you a rational thing. All right, what about x to the root 2? The way you do x to the root 2 is you write x to the root 2 as e to the root 2 log of x. And you use the chain. So this was a little something that people almost surely have slipped by them. Be aware of conditions and theorems. Okay? So for Friday's class, what I will do is I will do some stuff on sequences and series as a just general review. If there are specific things you want to see, let me know. I am trying to choose topics that literally cover as much as possible for the entire semester, as well as being worth doing. I mean, we just saw that base 2 is not the end-all be-all.